We've talked about buffers in the abstract and for mathematical systems, so it's time for us to talk about how buffers can exist in natural waters. So when we look at different kinds of systems, we have various freshwater sources, and these include lakes and rivers and streams, ponds, etc. We have brackish waters, which include river deltas and some swamps and marshes. And then we have true saltwater, which are our oceans and seas, and a few inland lakes, or inland trapped seas. But for the most part, we'll just kind of categorize them this way. So depending on how much stuff is dissolved in our water and what kind of stuff is dissolved in that water, we can end up having buffering in our natural waters or not. So if we think about what a buffer was in a laboratory setting, we have a weak acid and a conjugate base. And there's lots of things that can dissolve in water. We have lots of metal cations. We have lots of different anions of varying sorts, some of which can act like bases and some of which can't. Of course, we have H plus from various sources, OH minus from various sources, etc. But we have to have a weak acid and its conjugate base set up in that water in order to see any kind of buffering. The other thing that we have in natural waters is this: most water is going to be somewhere near 7 in pH. So we can't, have any old random buffer. We're going to have stuff that really is probably more in the 6 to 8 pH range, with a few that are going a little down and a few that are going to be a little bit higher in pH. But our pH range is fairly restricted, so the available systems that can buffer in this range are relatively limited. There are not a ton of different acids that buffer in this range. So those are our two requirements. First, that we have to have conjugate acid or weak acid and their conjugate base dissolved in our system, and two, that our pH range needs to be in their buffering range. So these are our two kind of big picture items. And when we look at seawater, of course we know that seawater is salty and it has a lot of sodium and a lot of chloride, but we may not know much else about it. So one of the interesting things for us to know is that oceans have a pH that's usually around 8.1, 8.2, so a little bit on the basic side, but that they've been absorbing carbon dioxide from the atmosphere at a pretty significant rate. And that over time, the pH of the ocean has started to drop a little bit. Now, if we think about carbon dioxide dissolving in water, we know that we've talked about this forming carbonic acid. We're just going to go ahead and assume that this dissolved carbon dioxide is the same thing as our carbonic acid. And we know that this can dissociate into H plus and HCO3 minus, which can also further dissociate into carbonate ion. And so depending on what our what our H plus is, these two equilibrium reactions will be somewhere in their sort of range. So what are some of the variables that are affecting the amount of carbonate, the amount of hydrogen carbonate, and the amount of carbon dioxide that's dissolved? So of course we know that Henry's law tells us that our concentration of any gas that's dissolved is going to depend on the partial pressure of that gas and on the Henry's law constant. And so when we look at the partial pressure of the gas, of course, this is measurable. This is a number, and we've been getting it from the Mauna Loa Observatory. But when we think about the Henry's law constant, we already know that this is temperature dependent. So it's the temperature of the water that matters. And if you look at ocean temperatures, they actually vary a lot. There's some pretty interesting maps if you do some searching on the NOAA website. Just search on ocean temperatures. And you'll see that if you look at the US southeast coast, some of the water temperatures there are pretty warm. They're like, right now anyway, they're 85 degrees or more in temperature. And of course, this is surface water. As you go deeper, it would of course get colder. If you look at our California coast, the water temperatures there are more like 65 degrees. It's still fairly cool. Puget Sound right now is in the 50s, depending on where you are. And this also, over on the Olympic coast, it's more like the California coast, around 65. But then if you look at the poles, so the Arctic and the Antarctic, these are going to stay closer to freezing. 0 degrees Celsius. Sorry, we're mixing our temperature degrees here. So if we think about how the Henry's law constant changed, we might remember that colder temperatures means that we have a higher concentration of our dissolved gas. And in this case, we're talking about carbon dioxide. So that means that in the Antarctic and the Arctic, we are going to have more carbon dioxide dissolving. And therefore, probably, we would end up seeing a lower ocean pH there than in some of our warmer ocean temperatures where less carbon dioxide is going to dissolve. And of course, we have to kind of keep a note here that deep water is colder. And in fact, deep ocean water is going to be pretty close to freezing. 0 to 3 degrees Celsius is kind of our average deep ocean temperatures. So the problem with the ocean becoming more acidic is that we have a lot of marine creatures that either depend on having carbonate so they can make their shells, or they eat creatures that depend on having carbonate to make their shells. So you might think about oysters as an example, or clams, or starfish. But there's also lots of plankton. And we know plankton is the root of our food chain in the ocean. And so if we have a problem with the plankton supply, this is going to travel up the food chain and have an impact on every single other organism that's in the ocean. So when we look at the way that these marine creatures are using the carbonate specifically, they often have a critical phase where the larval stage, so they go from an egg into a larval stage. And then if you look at creatures like oysters and clams, these often have a larval stage that floats around in the ocean, and then they may fix themselves to a rock. And it's in this larval stage that carbon dioxide is really super critical. So if they don't get enough carbonate during the larval stage, then they just die. Because they can't make a shell, they can't protect themselves, and they just die. So I put a couple of links to a video and an article that talk about the effect of carbonate levels in our local community. They're profiling a couple of shellfish farms in our region and looking at what the carbonate levels have been like and how the pH in the local ocean, which is colder and therefore is going to have a higher carbonate level, or excuse me, a higher carbon dioxide level and therefore a lower pH than some of the eastern seaboard. So we're seeing the effects of climate change earlier than some of the rest of the U.S. is. So those two articles, they are talking about what some of our local shellfish farms are doing to try to remediate. And most of their remediation happens in their fish or in their hatcheries, but this is a great example to see how farmers can have an impact on sustainability, and they're really partners if they do it right and if we do it right in preventing species extinction. So this is an interesting concept, right? You imagine that here we are, we're raising food to eat, and so ultimately we're planning to harvest these organisms. But on the other hand, because we happen to be intentionally raising these organisms, we are now potentially helping make sure that this species doesn't become extinct. So this actually is not the only situation where you'll see that happening. There are some interesting situations where you have game farms where people have a place where hunters can go, and they've imported livestock from, I don't know, say Africa, and so they have these antelopes, and then over time, the native habitat in Africa has become depleted, and that species is endangered in Africa. And because you have these farms where they've been raising these antelopes, there's now a genetic stock that's available to reseed the wild areas. So it's kind of an interesting, it's sort of counterintuitive. You don't normally think about farming, and especially raising of livestock, as potentially improving the chances of species survival. But this is one way that farmers can contribute. And so it's kind of cool to see this happening in our backyard. So I hope that you take a little bit of time and read through those articles, and then I'm going to have some more content here. But if you want to take a break now, this is probably a good place to do it and read those articles. So I wanted to talk more about some of the qualitative effects of these carbonate levels or carbon dioxide levels that are dissolved in the water too. And I'm going to lead you through calculations from a Journal of Chemical Education article that I posted onto the Moodle. You don't need to read the article separately if you don't want to. I'm going to lead you through the parts that I consider to be the most important or the most relevant to our class. But if you want to look at it in more detail, it's there for you as a resource. So let's talk a little tiny bit more about some of these qualitative measurements. So the local farms are now monitoring ocean pH. They are now amending their hatchery water both in terms of the pH and the carbonate levels in order to make sure that their larvae have enough carbonate to make their shells, and then they are seeding beaches with with young shellfish. And it turns out that it's mainly that larval stage that's super sensitive to the carbonate levels. But as you go to higher and higher carbonate levels, or excuse me, higher carbon dioxide levels and lower pH, if you get above about 600 parts per million in the atmosphere of carbon dioxide, then we're going to see that the ocean will become acidic enough that the shells will start dissolving. So that's kind of a problem. So one of the first concepts that I want to talk about before we really get into this article is to talk about the ocean and the aragonite levels. You'll hear them talk about this in the journal article, or excuse me, in one of the videos, and so I wanted to mention this. All right, so they talk about aragonite because it's one of the two solid forms of calcium carbonate. The other one is calcite. So calcium carbonate, this is the same as like limestone. And calcium carbonate is the solid that if it were dissolving, oh, I don't need that part, then we would be able to describe this system in terms of a KSP value, right? And we could look it up in our table and find out what this KSP value is. And in general, though, we can just see that this would be described in terms of the calcium concentration and the carbonate concentration. That would be our equilibrium constant value. Okay, so when people talk about oceans and the amount of carbonate that's dissolved in here, they talk about the saturation level of the oceans. And they talk about it in terms of a capital omega. This is the term they use for a capital omega. So if omega is equal to 1, then the ocean is in equilibrium in terms of its concentrations of carbonate with the calcium carbonate. So what we're seeing here is that if you took this KSP value for calcium carbonate and you put that in and then you said, okay, I assume that I have calcium carbonate, it's hanging out in the solution, and so some of it has dissolved, and the amounts that have dissolved are this X and X, and so I'm going to have X squared is equal to this KSP, and I'm going to take the square root, and that's my carbonate concentration. That would be assumed to be equivalent to the saturation level of omega is equal to 1. Okay, that would be the amount of carbonate concentration. And in actuality, the ocean really is supersaturated with carbonate. And it's supersaturated with carbonate, so this aids in shell formation. When you get down here to a saturation level of 1, then this is actually where shells start to dissolve. They're very much on the edge of what is going to stay in solution. So we really like the ocean to be more like oversaturated by a power of 3 in order for us to have healthy shell formation. And in most temperate waters, it has been at about an omega level of 3. So I wanted to make sure that you were familiar with this idea of the saturation level of the ocean. And And when they talk about the aragonite levels in the water, this is what they're talking about. They're talking about the saturation level of the ocean, that we want it to have a supersaturated or oversaturated solution of carbonate ion in order for shell formation to take place. Okay, so I'm going to end this video here just to make sure that it doesn't get too long, and then in the next one I'm going to go through the math that we talk about in the journal article and also in our textbook.